All right, page 221 in your textbooks, unit numbers 29 through 31, and looking at the transfer of thermal energy, we call it heat. And question number 29 says, what four factors determine the rate of heat conduction? Michael?
The four factors determine the rate of heat conduction is the constant of proportionality, the area, change in temperature, and change in length.
Okay, and the constant proportionality hinges on the type of material. Have you kind of realized that tends to be a consistent thing, whether it be tensile stress or thermal expansion, or here with rate of heat conduction? The type of material is what determines which constant proportionality we use. So, good, type of material, cross-sectional area length, and the temperature change, or temperature difference, you might say. Number 30. Name three materials that are especially good thermal conductors and three that are good thermal insulators. Audrey?
The materials that are good thermal conductors are diamond, silver, and gold. And three good thermal insulators are glass, wool, and I put plastic. That one's not too good.
I mean, you're looking at the chart, it's there on there. Okay, yeah, so I assume you were going off of the chart that was on page whatever that page was, 219. And the things that have really high numbers, like aluminum, copper, silver, they've got really high numbers, right? Those are going to be your good conductors of thermal energy. And the ones that have really small numbers, like cork is really small. Wood, like pine wood, is really low. Asbestos is dangerous and really low. Glass is kind of low, right? So that's what we were looking at for what is a good thermal conductor versus a good thermal insulator. I must say diamonds. She just has expensive taste. That's just what's on her mind. It's February, Valentine's month. Hey, a girl can hope, can't she? And anyway, number 30. Speaking of my new bulletin board going up, what are the odds? Anyway, it's my Valentine's Day board. What are the odds she says yes? What are the odds he asks me? What are the odds I get diamonds, okay? Most high school kids are just, I hope I get asked, or I hope he asks me, or I hope she says yes. And she's like, I want diamonds, okay? All right. All right, there we go. Number 31. Distinguish among conduction, convection, and radiation. Really, we're just kind of defining each. What did you have down for conduction? Kendall?
Convection is the motion transmitted between molecules at contact with each other.
Okay, so molecules in contact with each other, they transfer their thermal energy by contact. How about convection, Michael?
Convection is heat carried by moving material.
Good, like a moving fluid medium, not necessarily like a choo-choo train has, it's really hot, it comes into town, and so now this is hot because the choo-choo train moved in, but more moving fluid currents, good. And then radiation, Audrey, has nothing to do with the foot unless there's fungus that has, radioactive fungus on the foot. We were talking about that before we started. Anyway, ignore the foot, okay? Don't get hung up on the foot. It's a bad illustration. Audrey.
Radiation is emitted by excited molecules as they return to a less excited state.
That is one way to put it, yes. That's the way I think the book puts it. There's an easier way to define it. I'll give you my better understood definition. Anyway, the foot. All right. Let's review some things we talked about recently in talking about heat. We said there's a few different units we talked about we can measure heat in. Class, kind of call some of them out. BTUs.
Calories.
Joules, calories, good. Diamonds, no, not diamonds. All right. Joules, calories, BTUs, British thermal unit. Remember, that's the heat necessary to raise a pound of water 1 degree Fahrenheit, okay, because it's British units, at least formerly British units. By the way, Fahrenheit, I was thinking about this morning and thought, in Fahrenheit's defense, you're like, why did he use a saline solution to base everything off of? I think he was doing what Kelvin was trying to do, avoid negatives. Right? Because you know that salt water doesn't freeze readily, so if I set that as my zero, I'm not going to have to deal with negative temperatures very often. Okay, all right. So, I'm not as critical of Gabriel Fahrenheit anymore now that I had that epiphany moment. I'm sure he was smart like that, and then Kelvin's like, dude, we still have negatives. So you tried, but I got this. Hold my Coke. All right, anyway.
Saline solution.
Hold my saline solution. That would have been funnier. You need to become a teacher. All right. All right, teachers have to be quick on their feet. You are. You could be a good one day. All right, if that's what God calls you to. If He doesn't call you to that, then don't do it. Honestly, seriously, and don't be a teacher if God doesn't call you to. You're going to hate it. But if God does, you're going to have a blast. You won't get paid much, but you'll have a blast. And if you're honestly, truly, like you billionaires and billionaires commit suicide all the time. Famous, because money doesn't buy happiness. But doing something you love and doing what God's called you to do, you're going to be happy. You're not going to care that you don't have the nice stuff. No, I don't have super nice cars, but they get me from point A to point B. I don't have a nice house. It's a little crowded in there. We don't have a lot of space. We don't have a lot of stuff, so it's okay. But we're happy. We love what we do. We're having fun. Anyway, back to Gabriel Fahrenheit. Hold my saline solution. Anyway, so British thermal unit. That's how we get off on that. The calorie. What's a calorie? Heat required to raise a gram of water, 1 degree Celsius. It's a much smaller unit than the BTU, but BTU doesn't matter because we don't use it in science anyway. And then we tend to use the joule, which is an even smaller unit because it takes how many joules to make a calorie? About 4.84 joules to make a single calorie. So joules, very, very small units. That's how she got thinking about diamonds. It's my fault. We said that if we wanted to raise the temperature of an object 1 degree Celsius, that would be that object's heat capacity. The heat required to raise the temperature of a body 1 degree Celsius is the heat capacity. Now, every object has its own heat capacity, right? 5-carat diamonds, for instance, have a much higher heat capacity than a 1/4-carat diamond, which she sneezes at. Okay? She's like, no, I'll take that. Anyway, 5 carats over a 1/4 carat, right? And, if there's inclusions in the diamond, making it less, maybe that affects the heat capacity as well. So what we wanted to do was find the heat required to raise a single gram of the 5-carat diamond, 1 degree Celsius. That class we call the specific heat. Is the heat required to raise a gram of a substance 1 degree Celsius. And we use specific heat then, which is easily calculatable, has been calculated, documented on the internet, wherever you want to look for specific heats. We can use that then to find the heat needed to raise any object, any temperature. And what's the equation we use for heat, class?
Q equals CSP delta T.
There we go. Technically, capital C is heat capacity, lowercase c is specific heat. But since no one would think C, specific heat, add the SP to help us remember. Where we do need to remember, because our specific heats in our book are in joules per gram times degrees Celsius, mass has to be in grams for a change. We're so used to kilograms. Temperature has to be in degrees Celsius, which we're used to that already anyway. And of course, the heat will come out in joules. We said if objects are in contact with each other, they will reach thermal equilibrium as heat flows from the warmer object to the cooler object. We call this the law of heat exchange. In an isolated system, how can I quantify or algebraically represent in equation form the law of heat exchange? Kendall?
Negative Q loss equals Q gain.
And we worked several problems with this. Let's do one more together here. You'll do another one tonight for your homework. But you're on page 221 already. Let's look at problem number 18, or at least you were on page 221 before I told you to look at a different page. Problem number 18, go ahead and read that for us if you would, Michael.
A 2 kilogram block of iron at 100 degrees Celsius is dropped into a 0.75 kilogram of water containing 0.325 kilogram copper calorimeter cup. If the initial temperature of the water in cup is 12 degrees Celsius, what is the final temperature?
All right, so we have clearly a block of iron that is class,
100 degrees Celsius.
and it's going to do what?
Fall in water.
Fall in water. When it does, it's going to lose heat. There we go. That goes on the losing side. So we have the iron on the losing side. What's gaining heat from the iron?
The water and copper.
The water and the copper cup. All right, so we have negative Q iron equals Q H2O plus Q copper, okay? So that's basically what we're doing. And for every time we have, that's an O, not a U. It just looks like a U. For Q, every time, class, we're going to substitute C sub SP and delta T. So we have negative on the iron side, specific heat, mass, change in temperature. For water, specific heat, mass, change in temperature. For the copper, specific heat, mass, change in temperature. Over and over and over again. What is iron's specific heat?
470.
Flipping back a few pages, and Audrey looked it up, she said 0.470. How much mass was there of this iron?
2,000 grams.
2,000 grams. Good. 2 kilograms to 2,000 grams. I'm not going to write the grams. We just know how the units are going to play out. And then for the delta T, I said we must remember delta T is the binomial final minus initial. T sub F minus T sub I. Well, what does everything come out to, class?
Unknown.
Unknown. That's what we're finding. We're finding the T sub F. We do know initially the iron was at. So how should I write the temperature change? X minus 100. Final minus 100, which was the initial. Water, we know its specific heat. We know the mass of the water. 750 grams, right? 0.750 kilograms. So we're going to make that grams, 750. And the change in temperature.
X minus 12.
X minus 12. It started at 12 degrees, and it's going to end at the same equilibrium temperature that the iron does. The copper cup. Let's see, copper's specific heat.
0.390.
I was thinking it might be that. I felt like we did a couple copper problems recently. The mass of the cup. 325 grams, 0.325 kilograms, but 325 grams. By the way, technically, because we have Q's on both sides, if we had done kilograms each time, the decimals would have worked out okay. So technically, we could have gotten off the hook, but if we're just finding heat, we won't. So I like that we're getting in the habit of recognizing grams for the equation. That's the technical best thing to approach it with anyway. And then the change in temperature for the cup.
X minus 12.
Also X minus 12. Like the water, it was sitting there at 12 degrees. They were in thermal equilibrium with each other. And then, of course, we have the final temperature minus that. In all three cases, so I'm going to have to do what, class? Distribute. At your seats, finish the problem out. Cannot wait for it to dump out that vinegar. It reeks so bad. Audrey put on hand sanitizer like every 3 minutes. Good to go? Okay, checking your work. Did you get a negative 940 here that you distributed?
Yeah, I did 9,400 instead of 94,000, so.
Oh, well, you didn't add 2 zeros to the end.
Yeah,
Okay,
that was the only thing.
Yeah, that would make a big difference though, wouldn't it?
Yeah, I got 11.5.
Yeah, so it's like the temperature. Now, here's the way we catch it, right? You're like, the temperature went down. It was at 12 degrees. We dump on this super hot, scalding hot piece of iron, and it goes down? So you're like, I know 11 degrees is not right, okay? You got it? And you got it, and that was the only mistake. All the other numbers look good. All right, questions on law of heat exchange. But yesterday we began looking at the temperature of a body changing, and but we also talked about how a body can change states of matter. We specifically looked at water, and we said that as an object goes from the solid state to the liquid state, it must absorb a great deal of thermal energy to go from solid state, which is low energy vibration, to high energy free-flowing molecules. What do we call the heat needed to change from a solid to a liquid? Do you remember? The heat of fusion. And we call it because it doesn't change the temperature anymore. Like the temperature hits a certain level and it stops, more energy added causes the breakdown of the molecular structure, so to speak. We called it the what kind of heat? Heat that changes phase without changing temperature? Latent heat. The latent heat of fusion. And we said as well, if you had a liquid and you wanted to cause it to become a gas, you have to add even more energy to cause the molecules from freely flowing to freely flying. And what do we call the heat needed to vaporize a liquid? The heat of vaporization, or the latent heat of vaporization. Now, conversely, negative heat of vaporization would result in, right, which we call condensation, right? And negative heat of fusion would be freezing, right? We're going to work from the positive direction. And we said that this latent heat of fusion for water, do you remember what the number was? 333 joules for every gram of ice needed to be melted. And then the latent heat of vaporization, do you remember what this number was?
2,260.
Good, 2,260 joules per gram. Again, it takes a lot more energy to vaporize the liquid than it does to melt the ice into water. And you know this, right? Melting an ice cube doesn't take that long. Sometimes it goes way too quickly, right? And then, but boiling water seems to take forever just because it takes that much more heat, that much more thermal energy transfer. Look at your books. You're already on page 221 at problem 15. Page 221, problem 15. And read that for us, if you would, Audrey.
Calculate the heat required to change 50 grams of ice at -5 degrees Celsius to water at 30 degrees Celsius.
Now you realize there is a temperature change here, correct? But I can't just take ice and raise its temperature to water. What do I have to do with the ice before I can change it to 30-degree water? I got to get it to the melting point. So I can't just look at this and say, oh, well, the change in temperature here is 35 degrees, so CSPM delta T. No, I first have to go from -5 degrees Celsius ice to 0 degrees Celsius ice. I've got to get the water to the melting point first. Once it's at the melting point, what do I do with the ice? You melt it.
Yeah.
Add more heat until it melts. So the 0 degrees Celsius ice will turn into 0 degrees Celsius water. Once it is 0 degrees Celsius water, now I can raise its temperature up to what they want, 30 degrees. So I can go from 0 degrees Celsius water up to 30 degrees Celsius water. Do we see the progression? In order to make a phase change, you have to get the water to the substance to the right temperature to change phase, and then add additional latent heat to change the phase or state of matter before then continuing to change a temperature. Anytime there is a temperature change, though, as in these two cases, what equation do we use? Q equals C sub SP M delta T in both of these cases. But when you're C sub SP M delta T, but when we're changing states of matter, there's no temperature change. So it doesn't make sense to use this equation. That equation relies on a temperature change. There is no temperature change because it's not ordinary heat that's being added, it's what we call latent heat. So for a phase change, we're going to say that the heat required is equal to latent heat of, in this case, fusion times the mass. All right, so let's start by just getting the ice to the melting point. That shouldn't be too hard. We have to look back, though, and find what is the specific heat of ice, because ice has a different specific heat than water. Again, its molecules respond differently to heat than the molecules of water do because they're different. They're in a different arrangement. The mass is only, on number 15?
50 grams.
50 grams.
Okay.
Or you're looking at 16. 50 grams, which is a much smaller number, which means this won't be as hard. And then the temperature change, all we're trying to do is raise the temperature class 5 degrees. We weren't that far from the melting point to begin with. And so let's figure out how much thermal energy transfer, how much heat is needed to get to the melting point. Joules. Now, we're at the melting point. We got to melt all of this ice. That takes how many joules per gram? 333. And there's how many grams? So, how much thermal energy transfer is that? How much thermal energy must be absorbed? How much heat must flow?
16,650.
That's a lot of joules. All right, then we've got water now. It's a little puddle of melted ice that is still, for a brief moment, at 0 degrees Celsius, but it's continuing to absorb heat. And so the temperature is going to go up. Now that we have water, the specific heat is? We still have 50 grams of it. She's now in the liquid state, and we want to raise the temperature by how much? 30 degrees. So, how much heat? That can't be right. That's more like it. How much heat is needed? 6,270 joules to finish raising the temperature up to 30 degrees. So the question says how much heat's needed to go from negative 5 degrees Celsius ice to 30 degrees Celsius water. All I gotta do is add them up. And our answer,
23,432.5.
round it off to 2 sig figs, 3 sig figs,
23,400.
23,400 joules, or 23.4 kilojoules. Want to go that route? Or 2.34 E4 joules. I don't know, maybe it's just easier to write 23,400 joules. Considering zeros are easier to make than the K. Just a thought. Anyway, a lazy mathematician overanalyzing. They're like, what's the easiest way to write this? All right, questions on that? All right, number 16. Readeth that for us, Kendall.
Find the heat necessary to change 5 kilograms of water at 30 degrees Celsius to steam at 100 degrees Celsius.
All right, so we're starting, you said, with what?
Water.
At
30 degrees Celsius.
water at 30 degrees. Oh, so the 30 degrees Celsius water we just had? Huh. Okay. So we're going from 30 degrees Celsius water, and you said we're turning it into steam at 100 degrees Celsius steam. Can I go directly from water to steam, class? Not unless I'm at what point? The boiling point. The boiling point's where that happens. I'm not at the boiling point starting out. So what's the first thing I gotta do?
Water just 30 to 100.
Go from 30 to 100 Celsius with the water. Get it to the boiling point. At your seats, find out how much heat that takes. And it was how much water? 5 kilograms of water. Holy come on. All right. It's like 5 liters. Almost 2 gallons? Something like that. Not even a gallon and a half. Still, that's a lot of water. All right, how much heat is needed to get to the 100 degrees Celsius mark?
1,463,000.
That's a lot of joules, okay? Now, it's at 100 degrees Celsius. I want to go from 100 degrees Celsius water to 100 degrees Celsius steam. So, what do I do?
Multiply by the mass.
Latent heat of vaporization times the mass. That's an even bigger number. How much? 11,300,000 joules. And so if we add those, we can do that better without our calculator. What do we get?
12,763,000 joules.
And 3 sig figs again? You said? Yeah. So 1.27 E7. 1.28 E7 joules. That's a lot of water. It's going to take a lot of heat to get it up to vapor. And again, that's boiling all the water out of the pot. It's basically what we're doing here. Questions on this? Do we understand the process? Are we ready to put it all together and take it from ice all the way to steam? Feel like we know what we're doing step by step along the way. Get to the melting point, melt it. Get to the boiling point, boil it, and if necessary, superheat it. And we will do so. All right, so let's take a small sample size though, instead of, over a gallon of water. Let's take just a very small sample. Just a 10-gram sample. 10.0 grams of negative 5.00 degrees Celsius ice. And we want to turn that into 105 degrees Celsius superheated steam. Those are at least discolored.
price, I might get 30,244.
30,244.
Mm-hmm.
Did you get all the same individual numbers that I have?
I have, well, yeah, I have 4108.
Oh, okay.
Mm-hmm.
Kendall got it. Okay. So now, are you getting the same answer, Michael?
Mm-hmm.
Okay. All right. Checking the steps here. We go from -5 to the melting point, 102.5 joules. We go ahead and melt it, 3,330 joules. We then take this melted water and get it all the way up to the boiling point, 4,180 joules.
Mm-hmm.
Okay. What did you have?
I had 4,389.
So you did 4.18 times the mass of 10 grams times 100-degree change?
105.
Oh, okay. So you try to go all the way to the 105. You can't go to 105 with water. You have to get to 100 with water, and then once we evaporate it, we can raise it to the 105. Did you stop at this point, or did you keep going even though you'd already hit 105?
I kept going.
Okay, so you went ahead and vaporized it. You got the 22,600. I'm curious, what temperature change did you do here then?
I didn't.
Okay, so that's where you left off.
Yeah.
You just kind of left this step off because you said, well, I've already got 105. So, I mean, if 105 were the boiling point, at the point at which water would turn into steam, then you would have been exactly right. So, right, just stop it at the 100, go ahead and vaporize it, and then once you've got it vaporized, then you can superheat it to the next level. Does that make sense? All right, you'll practice this a little in your homework as well. We need to move quickly, though. Next thing in your notes, rate of heat flow. Rate of heat flow. You ever been stirring a pot of maybe pasta or something and noted that the spoon you're using starts getting rather warm? Now, some of that could be the boiling and the steam rising up off of it, but in theory, supposing we had a metal spoon in a pot of water, the heat would in fact travel through the handle. Or perhaps you've been cooking with a skillet with a metal handle, and the skillet itself, a cast iron skillet, the skillet itself gets hot, but the handle's going to get hot as well, correct? We're familiar with these, and so a lot of handles are made with some rubberized or silicone coating or something that's not going to allow the heat to flow through it. But think of it this way, if I use a little short spoon, heat is going to flow through a little short spoon faster than it would flow through a long-handled spoon. That's just common sense, right? Because the heat, the spoon is down in the hot liquid, that portion is going to attain thermal equilibrium rather quickly. But remember, those molecules are touching these molecules, which are touching these molecules, which are touching these molecules, which are touching... Do you get the idea? The heat is going to flow through the spoon. So we want to talk about the rate of heat flow. First of all, there are two categories of items. There are what are called thermal conductors. Thermal conductors. These allow heat to flow through them easily. Thermal conductors allow heat to flow through them easily. These are your metal pots and pans. They're metal because metal allows the heat to flow right through it very easily. The pot holders, on the other hand, are not good thermal conductors, right? You can set the hot dish down on the table as long as you put a pot holder under it because the pot holder is going to stop the heat from flowing through. Now, have you ever picked up a pot holder after it's had something sitting on it? It's very, very hot, isn't it? Well, that's because the heat got that far and stopped. It didn't necessarily flow through all the way. At least not the full heat flowed through, right? But metals, that's not the case. The metals, thermal energy goes right through it. Metals are very quick to adapt to different temperatures. Audrey helps me in PE, and we're putting together our metal soccer goals, the metal frame, and on cold days, they get real cold. Okay, they release their thermal energy to match thermal equilibrium with the environment very quickly. Those are thermal conductors. Usually metals are your good thermal conductors. Other substances don't allow thermal energy to flow through them easily, and these are called thermal insulators. thermal insulators. For instance, the cloth hot pads, right? Silicone grips, right? Don't allow the thermal energy to flow through them very easily. Wood does not quickly change temperature. So clothy substances, insulation, right, which just makes sense, right? The pink stuff that if you get it on you, it itches really bad later. That stuff that's up in the attic, right? That's a thermal insulator. It's designed in the wintertime that the heat that's in the house, it'll rise through the ceiling, which is made of, the drywall material, and it gets up to that pink stuff and it stops. The heat doesn't flow on through out into the environment, so you're not heating the world, and your electric bill goes sky high. Or in hot weather, the sun beats down upon the roof, the attic gets really, really hot, but the heat of the attic doesn't flow through that pink insulation down into the house as much, so that way the house doesn't get as hot. There's also usually insulation in the walls, particularly exterior walls. So although the walls get very hot from the sun beating down on the heat from the outside here in Georgia, the inside of the house doesn't get as hot. That fiberglass insulation is usually what it is, and it's those fibers of the glass that can get down in your pores and cause it to itch so bad. Anyway, so thermal conductors, thermal insulators. Rate of heat flow then depends on, first of all, the type of material. You'd rather stir the spaghetti with a plastic utensil, or better yet, a wooden or bamboo utensil, because it's not going to absorb the heat as quickly. It's not going to allow the thermal energy to just flow up through the handle as quickly. So the type of material certainly makes a difference. The length. And I'm going to say it this way, from end to end. And there's a reason I say it this way. The length from end to end. Because now think about a coat. End to end is actually the thickness of the coat, but we would consider that the length of the coat, right? From you to the outside air. How long is the conductor? Obviously, the thicker, the puffier the coat, the more protection you have from the outside cold to keep your own natural 97.5 degree body heat trapped inside, right? And so length meaning end to end. Certainly the temperature difference makes a difference. The temperature difference makes a difference, doesn't it? If it's really cold outside, even a thick coat is only going to keep you warm for so long. But if it's 55 degrees and you put on that big heavy coat, there's not a huge temperature difference to begin with. If you're stirring a pot of lukewarm water, even with a metal utensil, yeah, the thermal energy may flow a little bit, but it's not going to flow very quickly. Versus if it's boiling water, the thermal energy is going to flow a lot more rapidly. It just makes sense, right? The final factor is the cross-sectional area. This is how thick the stirring spoon is, if you will. This is how, really that's about the best example, because again, even with the pot holder, the thickness of the pot holder is actually the length from the hot pot to the countertop or tabletop. You don't want damage. That would be considered length. I guess the cross-sectional area, how the surface area, if you will, of the pot holder, the thickness of the spoon. That which is thicker has more atoms and molecules, which can then allow the thermal energy to flow through it more rapidly. It's like having a wider hallway, allows more students to flow through with more rapidity. So cross-sectional area makes a difference as well. The biggest one though, what kind of material is it? Different materials have different what are called thermal conductivities, and we see those over on page 219. And we referenced those earlier when we were going over the homework. Some substances allow thermal energy to flow through them really easily. Perhaps copper and silver would be the best examples of those. Aluminum's pretty high up there. Steel and lead are kind of low for metals, right? Brass is still pretty high, but steel and lead, some of the lower metals, they don't allow the heat to flow through them quite as easily. This is one of the reasons why, if you noticed cookware, a lot of cookware has copper bottom or all aluminum construction, right? Where cast iron, which iron is similar, steel is just refined iron, right? What's the guy, Rockefeller? When the steel, iron into steel guy. Anyway, similar construct. The cast iron skillet's going to take a little longer to heat up than is the aluminum pan. Aluminum pan is going to be quicker heating. Copper bottom is going to be even quicker heating because the thermal conductivity is higher. We don't have time, unfortunately, to get into the methods of heat transfer, so we'll have to save that for tomorrow. If we'd gotten started on time today, we would have had time, but anyway, my bad. Homework this evening is to complete a handout. Homework this evening is to complete a handout which will go over the math that we've covered here in section 4.3. So remember, we had 4.1 and 4.2, thermometry, temperature, introduction to thermal energy. We talked about thermal expansion. Then we changed gears, talked about heat. This is the math from the section on heat that you'll need to know. We'll go over this tomorrow. We'll finish going over methods of heat transfer. We are looking at a test coming up on Tuesday, just over chapter 14. So it's a short little chapter. As long as we nail down the math, this is a chance to do really, really well. Okay, so chapter 13 was a grueling chapter. Chapter 14, a much easier chapter. The two tests weigh the same, so a great opportunity to do well. That's coming up Tuesday. That's in lesson 112 is your next test. All right. Have a wonderful rest of your day.